My name is Kendall Hill from the University of Minnesota, Duluth. I've been working with my advisors, Dr. Diamond, Dr. Hedegaard, and Dr. Linderman on a load rating assessment of 3 concrete slab span bridges in Minneapolis, Minnesota. So a little bit of background on these 3 bridges. They're located on I-94 and I-694, crossing a small stream within the Twin Cities. They are all 3-span continuous slab span bridges. So that means they don't have girders. It's just a concrete slab going across a waterway. And the 3 bridges are currently load restricted. So that means certain classifications of vehicles aren't allowed to cross them. So they have to take a relatively long detour to get around them. And the Department of Transportation has identified this roadway as a critical trucking corridor. So it's really important for moving heavy freight across the state of Minnesota and across the Midwest. These bridges were constructed in the 1960s and then widened in the 1980s. So each bridge has the end spans are 23 foot 7 inches and the mid spans are 24 foot 2 inches. And the north and south bridges have a width of 72 feet, and the middle bridge has a width of 44 feet. The objectives of this project were to collect field data under a known load, which was a dump truck provided by the Department of Transportation filled with aggregate, develop and validate a finite element model of one of the bridges, and then evaluate that bridge's behavior and provide recommendations on the load rating, which will be given to the Department of Transportation. So the first step of this project, the finite element model, we developed 3 initial models, one using just elastic material properties, so the modulus of elasticity of the concrete, which we measured in the field by taking concrete cores from the bridge deck, and then 2 additional models that used inelastic material properties, so Menneray-Williams properties for uniaxial and biaxial compressive strength. In addition to that, we also modeled the steel reinforcement using isotropic multilinear hardening properties of the steel, so the yield strength, and then post-yield analysis. And then we also simulated 2-inch by 6-inch cracks within the model, and then 24 by 6-inch cracks in the other model. This was just to play with the cross-sectional stiffness of the bridge and identify what kind of behavior we might see in the field, because these bridges were relatively severely spalled and cracked. So we selected the middle bridge, the narrower of the 3, to conduct field testing on in June of 2021. So we performed a set of static truck tests as well as dynamic impact hammer tests to evaluate the strain and displacement under a known load, as well as acceleration to pull out the natural frequencies and mode shapes of the structure to compare to the finite element models. So using the initial models, we developed a set of static truck positions that we wanted to check out. We focused our testing on the northwest corner of the bridge. So we used truck positions at basically quarter points across the span of the first span, and then also positions at mid-span of each of the other 2 spans. And as I said, these were based on the initial finite element model. And then we also tested a set of paths going across the bridge. So 1 foot from the barrier, 4.5 feet from the barrier, 8 feet from the barrier, and then 16.5 feet from the barrier, which basically put the truck right in the middle of the bridge. And then also 1 foot from the far barrier away from where we focused our testing. We installed a big suite of instruments in the west span where we focused our testing. We did 15 strain gauges, as well as 4 linear variable displacement transducers, and 6 tilt meters. And then in each of the end spans, we had 5 accelerometers and then 2 accelerometers in the mid span for the dynamic testing, and then 10 LVDTs in the east span of the bridge. Here's a picture of us installing some of the equipment under the bridge. So you can see the long silver things. Those are the strain gauges. We used a 12-inch gauge length in order to account for some of the micro cracks in the bridge to give us a better value when we conducted our tests. And then you can see the LVDT. It's mounted to a tripod, and it's basically a big tube with a spring connected to a metal rod. And when the bridge moves, that metal rod will move up or down, and it will measure displacement for us. And then off to the left, you can see some of the tilt meters, which basically measured rotation in degrees of the bridge as it was loaded. So our static truck tests, we conducted a set of 53 different static truck tests based on the positions that I showed earlier. And then we also conducted a single truck tests as well as back-to-back truck tests. We had 2 dump trucks. Each were loaded to about 50 kips. And we used single truck tests, back-to-back truck tests, and side-to-side truck tests to evaluate the bridge behavior. And in addition to the static truck tests, as I mentioned, we conducted dynamic impact hammer testing. So over each of the 12 accelerometers that we installed on the bridge, we imparted 10 hammer strikes, ranging between 3,000 and 5,000 pounds of force on top of each of the accelerometers. So the accelerometers were installed on the underside of the deck, and we struck the bridge on the top of the deck. And this allowed us to measure the mode shapes and the frequencies after doing some analysis of the data. And we went ahead and compared that to the finite element model to verify if our boundary conditions that we initially assumed for the model were correct. We also calculated initial load distributions based on the field test for the bridge. So we used the displacement data and the strain data that we collected to determine how far across the bridge width each load was distributed, and compared this to the AASHTO models for the same value. And we found that the load distribution based on our field tests was between 40 and 80% greater than what AASHTO predicts for this bridge. So that means that the load rating could potentially be improved by that much. And right now we're continuing to update the finite element model using our field data. So this plot on the bottom right shows the black line, which is a set of displacement data from one of the truck tests. And then the other 3 lines are results from the finite element model, going through 3 iterations of it. And we're just trying to make that the finite element model match what we saw in the field. And that third red line is the closest one that we have so far, our 3rd iteration of the model. So what we're going to continue to do is finalize and update the finite element model using our 3D model. And once that's complete, we'll develop a simple plate or grillage model that can essentially do the same thing. And we'll provide that to the Department of Transportation for them to use on similar bridges throughout the state. And then we'll go ahead and assess the load rating of the bridges, and then provide recommendations to the Department of Transportation as to whether or not they can improve the load rating or keep it the same or possibly reduce it. But as I mentioned earlier, we saw that the load distribution from our initial field tests shows that the load distribution is anywhere from 40 to 80% greater than what AASHTO predicts, which will likely lead us to suggest an improved load rating. Thank you. Any questions?